Today we are going to talk about Android modding and hopefully learn a few things about how it affects the security of Android devices. First, a little bit about me. My name's Dan. I am a security consultant and vulnerability researcher at VSR right here in Boston. We do primarily application and network pen testing, code review, a lot of mobile assessments, things like that. I've published a few bugs, done a lot of work on Linux kernel exploitation, and most recently I've rooted a number of Android phones, and we'll talk about what that means. So the sort of overall goals I had for this talk were mostly to sort of clarify some of the terminology. You guys have probably all heard some of these terms being thrown around that we're going to use today, but they've frequently been thrown around in sort of misleading and confused ways. I hope to sort of demystify some of the process involved in rooting and modding Android devices, and then ideally we'll draw some conclusions about some of the security impacts of some of these modding techniques. So first, after giving a basic introduction to what the modding community is, who these people are, why they want to do it, we'll sort of start at the bottom and take a look at locked bootloaders, which is one mechanism carriers and handset manufacturers use to prevent running unauthorized code on these devices. Next, we'll take a look at some of the flashing protocols that are used to actually load new code onto Android phones. And we'll take a look at two case studies in actually rooting phones by looking at two exploits that I published. And then finally, we'll go into some of the modifications that you can do after having obtained root on a device and have some final thoughts. So first, just introducing the modding community. Why do people want to modify their phones? And sort of the most obvious reason, I think, is just to have administrative access, be able to gain access to all sorts of expert functionality. You need root privileges to perform tasks like do full disk backups and things like that, do free wireless tethering, free USB tethering. You can manipulate the balance between performance and battery life by overclocking or underclocking your CPU, things of that nature. The next big reason people want to mod is customization, just the ability to tinker with how your phone acts and behaves and looks. Another thing that sort of falls under this customization category is you're able to remove all these applications that carriers and device manufacturers put on your phone for advertising revenue that you can't otherwise take off. Sort of a less commonly cited reason that I think is useful for modifying these phones is maintaining upgradability. So one of the problems with the US cellular industry, in my opinion, is you have these heavily subsidized phones where you get expensive hardware that is given to you by carriers really cheap because you agree to a 2-year contract. But what that does is, every 2 years you're expected to ditch your phone and get a new one. So carriers incentivize users to treat these phones as discardable. And what happens is carriers halt support for devices very quickly in the Android world. So it's not uncommon to see a phone that came out, 8 to 12 months ago that's no longer receiving any updates from the carrier because it's not their newest flagship device. And if you take things into your own hands and mod your own phone, you can continually upgrade your device even in the absence of carrier support. And then the last reason people want to mod is sort of this basic idea of having freedom to do whatever you want to hardware that you've purchased. Now, given the sort of varied reasons why people want to mod their phones, there's a very diverse community interested in doing these things. This community mostly exists in online forums like XDA Developers, which has over 4 million users. Roots Wiki is another popular one that has something like 70,000 users, and Android Forums has another few 100,000. So it's a large community. But they're all of varying levels of technical background because you have people who are relatively talented hackers doing this stuff, and you have people who just want their phone to look kind of cool. And the result is you get a lot of mixed and confusing terminology. There's a lack of consistent definition of lots of terms that are used in modifying, and just a general, confusion. On the other side of the fence, you've got a number of parties who have a vested interest in not allowing you to perform unauthorized modification on your own phone, namely carriers and device manufacturers. One of the most popularly cited reasons for this is support costs. If everyone who didn't know what they were doing and turned their phone into a paperweight brought it forward for a warranty claim, that would cost carriers and device manufacturers some money. Obviously, carriers have a vested interest in not allowing you to remove sources of advertising revenue, and being able to tether your device for free, where free means you're already paying for the data, conflicts with existing carrier business models, many of which require you to pay extra for tethering. And then finally, the most commonly provided reason for why these carriers and OEMs want to prevent you from performing unauthorized modifications is security. And there's almost never any sort of explanation as to what kind of security they're providing, what guarantees do they want to achieve. And one of the points of this talk is to sort of take a look at this. So there are generally two strategies employed to prevent users from modding their phones. And the first is implemented in the operating system. So by default, most phones ship with an operating system that just has no mechanism built in to allow you to gain root access, to gain administrative access. And the second layer of protection is typically implemented at the hardware or firmware level by somehow preventing users from flashing new code to the device. And that's where we're going to start, taking a look at locked and unlocked bootloaders. So the term locked bootloader has come to encompass a pretty wide variety of restrictions that prevent customization on Android phones. But the definition that I'm going to use is a bootloader that performs cryptographic signature verification to prevent booting custom non-signed code. Now, the implementation of what a locked bootloader is and how it works will vary fairly dramatically based on vendor. So taking a look at the major phone OEMs, we've got Samsung, Motorola, HTC, and LG are the largest phone manufacturers of Android devices in the United States. And they have varied degrees of bootloader locking or unlocking. Samsung phones ship almost entirely unlockable out of the box. So if you buy a Samsung phone, you can rest assured that if you want to mod your device, you can unlock the bootloader yourself. HTC recently started compromising on this and supports an official unlocking mechanism that we'll talk about in a minute, where it voids your warranty, but it allows you to perform modifications if you want to. LG phones ship unlocked out of the box almost exclusively, but the way they prevent users from modifying is actually restricting access to various flashing protocols, so there's no way of loading unsigned code onto the phone, short of getting root on it. And then finally, Motorola is the most restrictive OEM. They have almost entirely locked bootloaders with no mechanism to unlock them, which means there is no way of running custom kernel code of any kind. So how locked bootloaders work, again, varies by hardware implementation, and this is sort of a theme. But the basic idea is that there's some sort of on-chip, as in the boot ROM, cryptographic verification of a digital signature on an early stage bootloader. So when you turn on the phone, the boot ROM does some sort of crypto verification of a signature before it passes off control to the early bootloader. And then the bootloader, in turn, will verify a digital signature on every subsequent stage of loading the operating system. So it will check any subsequent bootloaders and then eventually the kernel before it's run. So if the signature check fails, it either just fails to boot and turns off or drops into some sort of fail-safe mode for recovery. Now, before just taking a quick look at two implementations of this, I think going over the stock Android partition layout would be useful. So the actual partitions, once again, will vary by manufacturer and chipset, but there are a few that you'll see over and over again because they're essential to the running of the Android operating system. So you have your system partition, which contains native applications, system configuration, all your services, stuff like that. And this is typically mounted read-only by the operating system. You have your user data partition, which has all the juicy stuff, all your user-installed apps, your contacts, your data, basically anything that's mutable that was put on the phone by you after receiving it. You have your boot partition, which contains the kernel, and then the file system root, the RAM disk that represents the root of the file system with a number of other configuration-related things. The recovery partition contains the Android recovery system, which is sort of a fail-safe mode that allows you to do all sorts of diagnostic functionality. The cache file system has just various frequently accessed system data, and then the MISC file system is for odds and ends that's sometimes unused. So quickly, just to give you a better idea of what these locked bootloaders might look like in practice, one example that's been studied fairly extensively is the Motorola Milestone bootloader, which is a Motorola implementation on the OMAP chipset. And the way this works is the SHA-1 hash of the root public key is stored via eFuses, which are sort of programmable fuses that are implemented in hardware. And when the phone turns on, the boot ROM verifies this hash against the hash of a key that's stored in the first stage bootloader. And then if that hash verifies, then it will check the signature on the bootloader, which is called the MBM loader. Next, the MBM loader will verify the signature on MBM, which is the next stage bootloader, which will in turn verify the signature on LBL, which is the Linux bootloader, and then finally we'll verify the signature on either the normal Linux kernel or Android recovery. So the basic idea is, as I said before, you've got hardware cryptographic verification of a root public key, and then every stage of the boot process is cryptographically signed and verified. So if at any point you flash code, if you overwrite any of the bootloaders or overwrite the kernel and it's not signed by the vendor, then it will just not boot. And that's not readable right now, but this is from the Motorola Milestone wiki, which I have a reference to at the end if you're interested in this. Just another example of how this works in practice on HTC phones running more recent Qualcomm Snapdragon chipsets. The primary processor, which on these chipsets is the baseband processor, executes the PBL, which is the primary bootloader from ROM, and then it checks a Q fuse, which is another programmable hardware fuse, for this force trusted boot setting. And if that's set, it knows we need to enforce this signature chain, and it does basically the same thing. It loads a public key that's in the Q fuses, and then verifies the signature on the secondary bootloader, and then starts the app processor, verifies the signature on the H boot, which is the next bootloader, and then that verifies the signature on the kernel and boots into the operating system. Now, HTC actually has some additional protection mechanisms in place to prevent modding that's in the Android world called S-on and S-off. And what this comes down to is a NAND lock, so locking the flash memory at the hardware level to prevent writing to specific partitions, namely the system, kernel, and recovery partitions, which is where all the stuff essential to running the operating system lives. And the way this works is there's a flag in the radio NVRAM called the secu flag that's checked by hboot, which is that last stage bootloader. And if it's set, then it knows to lock this flash memory down. So if you want to flash custom ROMs to your phone or modify the system partition in any way, you need to either unset this flag or flash an hboot that doesn't enforce this restriction. And this is sort of that distinction that you may have heard of between temporary root and permanent root that people frequently use in the Android world. People use these terms outside of the HTC world, and they don't make sense there. And then lastly, we'll take a look at how HTC implements bootloader unlocking. So the way this works is you generate a unique token on your device, and then you send it off to HTC via like a website. And they'll keep that on record, and it'll void your warranty, and they'll send you a signed binary blob that is specific for your device that you will download and flash to your phone. And what this blob does is it's verified by hboot at boot time and will set a flag which will disable the signature checking. This is a pretty elegant solution that allows carriers and OEMs to get what they want in terms of support cost and minimizing them, but also allows users to modify their devices if they're willing to sacrifice their warranty. On phones that are unlockable out of the box, usually the protocol to unlock these phones is known as fastboot, which we'll talk about in a little more detail in a minute. If the device is unlockable, you just need to basically plug the phone in and say the magic words, which will unlock the phone. And this will turn off all the signature checking, and you can flash custom code however you see fit. And when you do this, importantly, this wipes the data partition on your phone, which is critical for data protection, because otherwise you could just take a stolen phone and then unlock it and flash custom code that boots into a compromised operating system that ignores any sort of device lock that you had previously set up. Next, we'll take a look at some of the protocols that are used to actually flash code to these devices. So there's, yet again, more Android fragmentation here. I know it's a buzzword, but it really does affect everything about the platform. So there are dozens of both proprietary and open source protocols that are used to flash code to these devices. The most common one is called fastboot. And this is sort of a standardized open source Android protocol that's used for flashing over USB. It's a very simple protocol. The client is a fast boot utility that's in the Android open source project, and the server, which is the part on the phone that actually receives these commands and does the flashing, is typically a proprietary OEM-specific implementation that's implemented in the second stage bootloader. And this protocol, basically all it does is it talks to the server and sends full disk images over the wire, which the server then just flashes to wherever you tell it. In most implementations, any sort of signature checking doesn't happen at the flashing stage. It happens when you boot the phone. So you can flash whatever you want, wherever you want, but no guarantee that your phone will ever turn on again. And then many phones actually disable access to this protocol to prevent this sort of flashing. The other officially supported Android update mechanism is called update.zip, and this is implemented in the Android recovery console. You can boot into it, and there's an option like flash update from SD card, it's probably called. And all this does, you copy a zip file to your SD card or internal storage, and this zip file contains some metadata that tells it how to perform the update, and either full binaries or a binary diff, and it validates an RSA signature against manufacturer keys stored in your device, and then will apply the update. There have actually been bugs in the past in this mechanism. The original Droid root was due to a problem where you could actually concatenate two update.zip files and tinker with a few bytes to cause it to verify the signature on the first half and then apply the update from the second half. Next, Tegra devices, NVIDIA Tegra, have their own boot protocol, or flash protocol, called APX mode, and the flashing protocol is NVFlash. So this is actually implemented in the boot ROM, so by the hardware, not the firmware bootloader. And the way this works is all communication is AES encrypted using what's called the secure boot key, SBK. And this is also implemented in hardware as blown fuses. So these are ideally secret values that no one is supposed to know, but in reality, because of the interest in modding these devices, these secret values are leaked pretty commonly, either leaked by the vendor or someone working for the vendor, or sometimes it's found that they're based on the device ID. The way this protocol works is you upload a RAM disk containing a minimal bootloader, and then that handles the actual flashing. Next, yet another protocol, Motorola's SBF, is very similar to NVFlash. It's implemented in a bootloader instead of the boot ROM. The client is RSD Lite. The RAM disk is signature checked, and it's gone away, mostly replaced by fastboot. And then finally, you've got a few more flashing protocols. LG has their own, Samsung has their own, Pantech has their own, and HTC has another flashing protocol called RUU, which is basically just fastboot. So you can see that there's a pretty wide range of protocols here. So key takeaway points from all this. The user data partition is what contains basically everything of value on your device. It has all your contacts, all your mail, your SMS, apps, application data. And the other thing is that all these flashing protocols are reachable prior to booting the actual operating system. So setting a device passcode by itself won't save you if a user has the ability to use these flashing protocols. That being said, if you're not using any sort of disk encryption, that means all of your data is going to be recoverable no matter what you do in a few situations. Namely, if you're using a Tegra device and the secure boot key of that device has been leaked, then anyone can boot your phone into APX mode and use NVFlash to read all of the data off your phone, and there's nothing you can do to stop that. If the bootloader is maintained in an unlocked state, then there is nothing you can do to prevent someone from getting all of the data off your phone. Because an attacker could take your stolen phone, flash a compromised kernel or a compromised system partition or compromised recovery system, boot into that, and then dump all your data. Now, on the other hand, if you're using disk encryption, then the status of the bootloader has absolutely no effect on data protection, because even if they can compromise your device and cause it to boot into an evil operating system, the disk won't be decrypted unless you provide your password. And this, of course, depends on actually using a strong password. A 4-digit numeric password for disk encryption is totally useless. All right, so next we're going to move on a little bit up the stack into the operating system, rooting devices. So why do people need to gain root access on their devices? I mean, obviously, you want root access to be able to perform administrative tasks. But also, in the sort of greater picture of modding, it's possible to have a device like LG phones where they have an unlocked bootloader that supports actually running custom operating systems, but they don't have a way exposed to actually flash unsigned code. So the only way to do so is by rooting the device. And then finally, on devices that have locked bootloaders like Motorola phones, you really have no degree of customization unless you root the phone. So going into a little bit of background that's necessary to understand some of these vulnerabilities we'll be talking about in a minute. ADB is the Android debugging bridge. You connect over Wi-Fi or USB, and you can turn on support for this by flipping a switch in your Android settings, USB debugging mode. And this protocol allows you to install and uninstall applications, and more importantly for our purposes, it gives you a shell on the phone. And this shell has user ID, group ID shell, and a whole lot of supplementary groups, like the log group, internet, graphics, Bluetooth, and mount. Next, the other little Android trivia that you need to understand before going into these exploits. Android has a system called properties. The short version is it just uses properties to store global system settings. And applications can set arbitrary properties except for certain reserved namespaces, like RO properties, read-only properties. These properties can be set only once, and once they're set, you can't change them. And then finally, putting these pieces together, ADB and certain properties interact with each other in specific ways. So if the ro.secure property is set to 0, then the ADB shell will run as root instead of shell. There's a lesser known interaction here though. If this ro.kernel.qemu property is set to 1, ADB shell also runs as root. And this is just a little comment from the ADB shell. This is designed to give root access to the emulator. Having that under our belts, we can start talking about these two exploits that I wrote that rooted phones. So this is Moto fail. It affected basically every Motorola device up till that point. So the goal of this exploit is to gain root, obviously. But the way we're going to do that is realize that the Android init process, like the first process that starts when your phone turns on, parses this file for property settings when it turns on. It's this data local.prop file. And this just contains key value pairs of, this property equals this. And if we can modify this file to set any of the previously mentioned properties, like ro.kernel.qemu, then we'll win, because our ADB shell will then run as root, and we'll have root access to the device. Fortunately, there are a lot of file permission bugs on Android that will allow us to do this. In particular, the bugs that I used for this exploit are in the init.rc script, which is just an initialization script that's parsed by the init process. So this script had multiple bugs. So first, they create this don't panic directory, which is accessible by the log user, which our ADB shell has access to. They create this logger directory. Then they move a file from one directory to another within two directories that are writable by us. So what we can do here is put a file containing this ro.kernel.qemu equals 1 at the source of that copy, put a symbolic link pointing to that local.prop file at the destination of the copy, and then when we reboot the phone, the init process will copy our file on top of local.prop, and we'll have set that property, and the ADB shell will run as root. Now, something that I really enjoyed about this exploit was I threw in a little bit extra. There is this adversarial relationship between people interested in rooting their phones and the device manufacturers, because the goal of people rooting phones is to keep these bugs unpatched as long as possible so people can actually continue to use it. So to prevent patching, I threw in some tricks to this exploit. It was shipped as just an ELF binary, and it actually was a custom emulator that I wrote with a made-up assembly language that read the actual exploit as data that looked like gibberish and evaluated it at runtime. And it had a bunch of dirty tricks to prevent dynamic analysis, and had all this dummy code generation for throwing people on false trails, and included the full list of the entire file system in the binary just to screw with people a little more. Motorola fixed it pretty quickly anyway. I'm not sure if it's because they already knew about the bug and had just not rolled out the fix yet, or if they hired someone to fix this. But if you were the one who actually had to reverse engineer this, please email me. I'd love to talk with you about it. So we can learn a few lessons from this. First, file permission bugs are a fairly serious problem on Android. Unlike on iOS, where you have some degree of real sandboxing, where applications are restricted to a fairly confined environment, Android, the restriction is done by user ID. But there are several directories that are accessible by everyone. I've published, I think, 10 root exploits at this point for Android, and of those, I would say 9 of them are just simple, stupid file system bugs, like where you have a world writable directory and some privileged process is performing actions on something in that directory, and you can cause that privileged process to do something on your behalf. And many of these these bugs are created by the OEMs, not Android, not Google. The next thing to take away here is that this exploit isn't possible without the log group. And this was actually the case with many of the bugs that I encountered. This group is actually granted to applications that request the android.permission.readlogs permission. And in my experience, this permission in particular substantially increases the attack surface exposed to malicious applications. So you should be very wary of granting this privilege to any application that you don't fully trust. Additionally, there's been lots of documented problems with applications logging sensitive information to the Android debug logs, which this permission gives you access to read. And then finally, another important lesson here is you really want to disable USB debugging mode if it's not in use. Because if you leave it enabled, someone can pick up your device, plug it in, gain access to a shell via ADB without bypassing your device lock, and then root the phone using an exploit like this to gain access to all your data. The next exploit we're going to look at is the one I published for the Sony Tablet S. So the bug here was, again, simple and stupid. There was a log directory, and it's writable by group log, and this directory contained all these root-owned files that were being written by this logging service that are on-disk copies of the Android debug log, and they were created with predictable file names. So I noticed that if you replace one of these backups with a symbolic link to a target, when you trigger a log dump by just flooding the log and causing it to write that out to disk, it will either create a new file anywhere with the contents of the log, if the target of the sim link didn't exist, or append log contents to any existing file. So we can develop a plan of attack using this capability. The ultimate goal here is to get that string ro.kernel.qemu=1 into data local.prop, because that causes ADB to run as root and allows us to win. On any other device, this would be really easy. We control the log file contents because we can write to the Android debug logs as an application. If this local.prop file didn't exist, then the vulnerability would create it for us, and if it did exist, the vulnerability would append to it. But on this particular device, and this is the only device I've ever seen this on, they actually had instead of a file at local.prop, it was a symbolic link to a read-only configuration partition. So we couldn't append to that file because the file system was mounted read-only. So in order to make this work, I needed to find a way to remove an existing symbolic link and create a new file there. So I spent a few weeks thinking about this, how I could leverage this logging vulnerability to remove a file rather than just create one. And I noticed an odd behavior that the Android Packager Manager has. PM distinguishes between these system and user-installed applications, where user-installed applications are installed on the data partition, and system applications are installed by the OEM on the read-only system partition. Now on Android, every application has a data directory in the data, com.myapp.whatever directory. And inside here is a lib directory that is designed to have native libraries if your application has any. But system applications are expected to have an empty lib directory because all of their libraries are supposed to be on the system partition. And the package manager actually empties a system library's lib directory on boot if it's not empty. So I was thinking, what happens if we replace a system app's lib directory with a symbolic link to a directory that we want to be empty? It turns out the package manager will follow that symlink and empty that directory. So that's a possible vector to delete files, but how do we run code as a system app? We can't just magically remove that directory there. There's a program on Android called run as that allows the ADB shell to assume the privileges of any application that's marked as debuggable. And the way it determines this is it parses this packages.list file to check the status and UID of the package and see if it's marked as debuggable. And normally, no system application would ever be marked as debuggable. But because we have this logging vulnerability, we can actually append data to arbitrary files, so we can modify this packages.list file to make a system app debuggable. And this is what happens when you put all of this together. You trigger your log vulnerability to append like fake package information to this packages.list file that will allow us to use the run as program to assume the privileges of a system app. Then we replace that system app's lib directory with a symbolic link to the data partition, reboot, and then the package manager will remove datalocal.prop when it comes back up. Next, we can use the log vulnerability one more time to create a new local.prop file with our ro.kernel.kimu equals 1 property, reboot again, and ADB will run as root, and you win. We can take a few lessons out of this whole thing, too. So frequently, it's a little bit questionable as to whether root vulnerabilities are actually security vulnerabilities, because this vuln in particular can't be exploited by malicious applications in any way. You need to use run as, which isn't accessible by applications, in order to exploit this. One thing I noticed over the course of the past few months is frequently these sort of benign roots that are not exploitable by malicious applications are frequently patched faster than real security bugs, like bugs in the WebKit browser that actually could be used to really own people. And to be fair, a lot of these bugs are caused in OEM code, so the patch lifecycle is a little bit shorter, but it's still a little bit suspicious for me. And then finally, it's very common for multiple bugs or techniques to be chained together to achieve a goal here. So now that we've talked about what root exploits actually look like, there are a few things you can do on your phone once you've achieved root. The first thing many people do is install a custom recovery partition that replaces the stock Android recovery system, and this just allows you to easily and safely flash custom kernels and things like that. The most popular of these is Clockwork Mod Recovery, which is CWM, but if the bootloader is locked, you can't flash a custom recovery partition because it will fail to boot. Instead, one of the things you can do is hijack the original recovery executable, which is on the unsigned system partition, and this is called a bootstrap recovery. A few more techniques that are commonly used on phones that have locked bootloaders. Second init is a clever technique that actually uses the ptrace system call to hijack the init process very early on in boot, just to allow you to run custom initialization scripts without the whole system having to come up first. Second system is another sort of clever trick where rather than modifying a system partition, they just mount a new one right on top of it and preserve the original. And then finally, some people use the kexec system call, which is a Linux system call that allows you to actually run a kernel directly from memory without flashing it to disk. This is sort of less commonly used because usually there's all sorts of hardware setup that needs to happen during the boot process that this skips over, and it makes it very difficult to make it stable. Next, we'll talk about how root access is actually provisioned on these devices. Once you've achieved root via an exploit like the ones we just talked about, how do you maintain root access to your device, and how do you grant root access to applications in a safe way? And the answer, most commonly, is the SU and superuser applications. So on Android, there are no account passwords per se. The way SU and superuser works is SU is just a setuid root binary, and superuser is an ordinary Android package. And the way applications request root is they execute SU, and SU communicates with the superuser package over a Unix socket to check its database of permitted applications and user IDs. And it has a database of permit, deny, or prompt responses. So if you grant privileges to a certain app to do certain things, You can set it so that it always allows that, or set it to always prompt you, things like that. And this is a fairly reasonable solution to making sure that the user actually has a say in what applications are granted root privileges. Unfortunately, SU does increase the attack surface of your phone. By default, on Android, there are no setuid binaries that are accessible by applications. And history has shown that the mere presence of setuid binaries can enable exploitation of privilege escalation vulnerabilities. For example, in 2010, Tavis Ormandy had two very cool glibc vulnerabilities that both required setuid applications in order to exploit. And more recently, a bug that actually affected Android, CVE 2012-56, was a Linux kernel privilege escalation that was ported to an Android exploit called mempodroid. And again, this required a setuid application to exploit. So this would not be exploitable by malicious applications unless you had rooted your phone. Additionally, it's important to take a look at SU because it's a setuid root application. Maybe it has vulnerabilities of its own. One thing that I really don't like about it is that it grants root privileges automatically without asking to the shell user. And finally, I just looked at the code recently and it looks okay now, but there has definitely been some really questionable code quality in this program in the past. A couple months ago, they fixed probably the most trivial stack-based buffer overflow in existence in this setuid root program. So just wrapping all that up, if USB debugging mode is enabled and you have SU installed, an attacker no longer needs a root exploit to gain access to all your data. So that's definitely something to keep in mind. Having SU has its benefits. If you have root access on your phone, you can patch your own services. You can much more easily detect malicious activity. But typically, people don't do that. And then finally, it does introduce additional attack surface via potential vulnerabilities and the presence of accessible setuid applications. So that's about it. Just some final takeaway points from all of this. One of the things that I really want to emphasize is it's impossible to evaluate Android security on the whole because of fragmentation. And this extends way beyond just software patching. When you're considering Android security, either for an enterprise or for personal usage, you really need to take a look at the chipset and handset manufacturer, because depending on what bootloader technology is used and what flashing protocols are available, that really affects the data protection on the device. Next, you should absolutely use disk encryption if it's available. It was implemented in Honeycomb, Android 3.0, and is much more accessible in Ice Cream Sandwich, so hopefully more devices will have easy access to that. Use a strong password. If you use ADB frequently, disable USB debugging access when you don't need it, because this is just a backdoor channel into your phone. And then finally, rooting and modding is obviously a double-edged sword. If you're a very security-conscious user, it can give you more power in locking down your device. You can continue to upgrade your phone in the absence of carrier updates and fix vulnerabilities yourself, but it may introduce additional vulnerabilities and exposures. So thanks to a bunch of people from the Android community who answered questions on stuff. These are a few references that are really detailed documentation on some of the HTC bootloader process and some of the reverse engineering that's been done on the Motorola bootloaders. And any questions? Yeah, sure. I can hang out on this one if there are any questions. Nothing. Yes? Well, I think a lot. Okay, sure. Yeah, thanks. The question was basically, why reinvent the wheel? Why don't we just reintroduce passwords onto Android so that can be our way of provisioning access to privileged accounts? I think a lot of that is actually in the design of Android as a platform rather than the modding community. The actual stock Android operating system doesn't have support for those passwords. So I think that's really a design decision that was made by Google. to allow it to be easier for applications to run as separate user IDs and not have all sorts of crazy transitions between those unprivileged accounts. You'd have to ask them. Yes? It would be easy to implement. I've used one before, but yeah, you're right. I think yeah, I mean, it would be good to have a password, but on these phones, the more important thing is that the user has control. So as long as it presents a prompt to the user that is presumably only accessible after any sort of device lock has been opened, then I think it accomplishes the same purpose. Yeah. Well, I think you should go to the talk tomorrow. The Mobile Exploit Intelligence Project probably talks about that a little bit. Yeah, most of the malicious payloads use a very small number of publicly released exploits. I know Rage Against the Cage was Sebastian Kramer's exploit that was turned up in some malware. None of my exploits have ever been used maliciously because, with the exception of one that was very specific and an egregious vulnerability, none of them are possible to exploit from an application. And I think if you're interested in contributing to the rooting community, it's important to make those decisions carefully about what you release and realize what is risky for users and what is not. Does that answer the question? Oh, I have not heard of anything like that, but I think that's something that people should definitely be concerned about. For example, the MotoFail exploit that I released was a native binary that was designed so that no one would have any idea how it worked, and thousands of people ran it on their phones. And I think that speaks to a risk there, that users are willing to just run code if you put it out there and say that it'll do something good for them. I guess they trust me. Any other questions? All right, I have to put this up because I'm a good source speaker. There is a survey for a feedback form. And thanks for coming out.